Alright, good evening Year 9s. Welcome to topic 5 of our Geology unit. We're going to look at some of the mechanisms behind tectonic theory. So our last video we covered what it is and what it described. This time we're going to explain more the how it actually works. So here's our Walton, our Wilf. So we want to look at the internal structure of the Earth, what continental drift actually is, and how convection drives this process of continental drift. So we want to be able to label and describe the planet and explain how these things actually, how convection currents actually cause continental drift. The reason we're doing this is when tectonic theory was originally proposed by Alfred Wegener, it was sort of thrown out partly because people thought the idea was just crazy. But the second part was that they couldn't explain why or how it actually worked. One big thing with science is it's very well to say, oh yeah, this is it, but if you can't explain the process or the causes for it, it's very hard to do any testing. As we learnt more about the Earth and we discovered convection currents, it helped explain, oh well, this would actually be a mechanism for how this could work, and so it started to gain a bit more acceptance along with that other evidence that we talked about in our previous video. So the Earth's structure, you would have seen a bit of this last year in Year 8 Geology. We've got the crust, the mantle. Now in this year we're going to talk about the outer mantle and the inner mantle, and you may have also talked about the outer core and the inner core. So you might have seen just crust, mantle and core, or you might have seen crust, mantle, outer and inner core, or perhaps you saw all 5. Have a look at the video. It's a bit cheesy, but it does sort of talk about the differences at each of these layers. Now, here's more of a descriptive version of it. A crust, hard rocky layer. We stand on the crust, we're kind of familiar with the crust. The upper mantle, or the outer mantle, is a it's only 350 kilometres thick, so compared to the Earth it's quite thin. It's a thin solid section with some molten rock under it. The inner mantle goes very deep. It's a much thicker form of lava. Now, don't mistake this as anything like liquid like the inside of an egg. I mean, it's still rock. It's just really, really hot rock and very, very dense that happens to slide past itself a bit more. Then we get down to the outer core, which is a fluid of mostly iron and nickel, and then the inner core is solid iron. And what's kind of cool there is, even though it's hotter than the outer core, it's solid because the pressure around it is so immense that that condenses it back to being a solid instead of being a liquid. Now, those 5 layers, they're grouped mostly on composition. Okay, what they're made of, so what elements we find. And we're going to have a look at that in a little detail for a second. You don't need to memorize them, but I do want you to sort of understand it. The other way is to look at the physical state and the mechanical properties. So we're going to look at the Earth in 2 different ways this year. Last year you looked at it from a composition point of view. This year we're going to look at a composition and mechanical, and you might have had some of these words for the mechanical part last year. So this is kind of a cross-section view of the Earth. Now, you might be able to see the elements. However, remember you can access this PowerPoint on eLearn. Atmosphere, don't worry about that, that's the gases. But the crust, you've got oxygen, silicon, aluminium, iron, calcium, sodium, potassium. We go down to the next level, we find plastic magnesium, so that's magnesium that's in a sort of plasticky state because of how hot it is. Iron, aluminium, silicon, and oxygen. As we keep going down, we get different things: olivine, pyroxene, and feldspar in the lower mantle. Outer core gives us liquid iron, sulfur, and nickel, and then in the inner core it's just solid iron and nickel. So you get different stuff, you get different elements, and as you saw with those mantles, different compounds are at different layers within the Earth, and that's what gives us this layer approach. Now, here is a diagram, and you can see here we've got our mantle, we've got our crust, and we've got our core. Now these haven't been split up into the outer mantle and inner mantle, and the outer core and the inner core. Over here we have our outer and our inner core. These bits here, the core, we're not really worrying about this year, but here you can see there's a few new names. We've got mesosphere, we've got asthenosphere and lithosphere. There's also the hydrosphere and the atmosphere, but they're year 10 that we're going to be worrying about that. And you might have sort of clued on there that they're all spheres. They've all got that same root word at the end. In this case, we're talking about circles of things, or three-dimensional circles of things, to be in reference to a sphere. And the ones that we're mostly going to worry about for you guys, the lithosphere here at the top and the asthenosphere right underneath it. So we're only really dealing with this first 400 or so kilometres. So the lithosphere comes from the word Greek lithos, meaning rocky, and it is the crust and the upper part of the mantle of the Earth, so it's all the rigid part. Asthenosphere comes from the Greek asthenes, meaning weak, okay, and it's the viscous mantle. So remember, viscous means very slow running liquid. Something with low viscosity runs very easily. Something with high something with high viscosity runs very stickily. Right? And this is the section underneath the lithosphere here that sort of moves, but it's very, very slow. It's kind of like how if you've got honey and you cool it down. I know, getting cold in Brisbane's a bit of a hard thing, but when we're getting close to winter, we're in autumn now, we could take this, we could cool it down, and it slowly moves. There's actually a very famous experiment that's been going on at UQ for a very long time, looking at the viscosity of a substance called pitch. And in the actually, I'm going to Google it. How long has the pitch experiment going? How long pitch drop experiment UQ? It started in 1927. Okay, and in 1927, Professor Parnell, he heated a sample of pitch, put it in a glass funnel, let it settle for 3 years, okay, and then he cut the bottom off of the stem so that it could drip out the funnel. And it's been dripping since 1927. It's 2020 at the moment, so it's nearly 100 years of this experiment. And I think it's been like 9 drops. The last drop fell in April 2014. The next one should be sometime this decade. And what seems to be the unfortunate consequence of this experiment is the people who take care of it never actually get to see the drops. And it always seems to be that when a drop is about to happen, computer issues cause. You can actually go and look at it. It is at UQ, and if you ever go to UQ, you would be able to see it. However, it's a very, very viscous material. So imagine something there that takes decades before you get a single drop of it forming. Okay, and this is sort of the bit of the asthenosphere underneath the lithosphere. When we say it's liquidy, when we say it's viscous and it's not a solid, people tend to think about, oh, it's like water. Or you might think about the kind of molten lava right at the very top of a volcano that you see in movies. No, like it's a very viscous material, and it's very slow moving. We don't have great ability to conceptualize geological time in our common time frame. So when we say it's running or it's moving at such an extreme long process. And so here's a different way of drawing it here. So I would recommend you draw this because it helps you see that the lithosphere is connected to these two, the continental crust and the rigid mantle. There's also oceanic crust, and we're going to get into the difference between these two shortly. While asthenosphere down here is part of this convecting mantle, and the convecting mantle is where those convection currents are, which we'll get to in a moment. Rigid, remember in this case, means it's solid, it's not moving, it's just kind of there for the ride. Here's again compositional versus state structure, crust and mantle. You see the lithosphere goes a bit into the mantle, the asthenosphere is just this top part, and then the mesosphere is the bottom part of the mantle. You can feel free to remember the mesosphere, but it's not really something we focus on much this year. Even if you just remember the name as being below the asthenosphere is perfectly fine. So we need to talk about what these convection currents are, because we've talked about the structure, but how does this move? So a convection current is an area where a fluid, now in science a fluid means either a gas or a liquid, because they both flow, so they're called fluids, where we heat an area of fluid. And the area that is hot will start to expand and rise. Now if something rises and gets out of the way, that means there's going to be a place for something to come in underneath it. And so as it rises up, liquid flows in underneath it onto the heating area. When the fluid can't get any further, it gets to the top and then it spreads out. It contracts and then it falls back to the bottom and it repeats itself in a cycle. You can do this at home. What you're going to need is a pot of water, and you're going to need a few grains of rice. If you get your grains of rice and you put them in the middle of your pot of water and you heat it up, what you'll find is that the rice will rise to the top, spread apart, then fall to the bottom. Barley or oats, any sort of grain cereal, is another good thing that you can use for this. If you've got a pot that is bigger than your heating element, that also really helps demonstrate this for yourself. Now, and we'll see this when we get back to school after lockdown finishes, so I will show you this as well. But here's an example of this with a diagram of a Bunsen burner. So you can see here we've got our Bunsen burner, it's heating up the middle, the water is rising, gets to the top, spreads down, and then as it cools it starts to sink again, and we get this cycling effect. And the same thing happens in the earth. Here we have an area where at A, the heat is causing the rock to come up, gets to the top, can't go any higher, gets pushed to the side, and then gets a bit, cools down, falls to the ground, or falls deeper into the earth, and the cycle repeats. And it's this slow moving of this viscous liquid that drags the plate along and on top. And so as the fluid spreads out, the earth moves with it. If the earth tears, some molten rock comes through as a volcano, and it keeps creating new crust for us. However, it will then drag that crust either side, tear it apart, create new crust. Here's the diagram on sort of a larger scale, and so you can see here we have heat from the core rising up through the mantle. You might get a little bit coming through that ridges that we talked about in our first videos, and then the molten rock moves to the side and it drags the lithosphere with it, and eventually you get some points where it subducts under the ground, and we'll talk about those boundaries in our next video. Now the last part of this is sort of go, well, where's the heat come from? Because heat eventually runs out. If I'm heating a pot and then I turn off the oven, well, the pot will stay hot for a little bit. There'll be heat in the middle transferring through into the whatever I'm cooking, but eventually that heat will be equalized and I will no longer be able to get heat out. So where does the heat in the earth keep coming from? A few places. The earth, the core of the earth is still cooling down from when it was made. It's only a balmy 6,000 degrees Celsius, about the surface of the sun. But there's some other things that produce heat. Radioactive decay, which we'll be talking about in our next unit, that releases energy, and it's a similar process, just the opposite end of the process that our sun uses to produce energy. So radioactive decay releases energy, and that keeps things nice and warm, same way that nuclear power plants work. And then the mantle as well will release some energy, and that will end up contributing to the heat of the asthenosphere. So at its core we have a heating process, and that heating process causes a convection current inside the earth, and those convection currents move the asthenosphere over the top of it. Alright guys, that is the end of this video. Thanks very much for listening, and I'll see you soon. Bye.